In Module 10, Section 5, we will solve equations containing rational expressions. In order to do so, we will clear the fractions by multiplying both sides of the equation by the LCD of all the fractions and solve the simplified equation as we have in previous sections. Let's try an example. 5 over 3x plus 1 equals 7 over 6. Let's start by making the whole number a fraction, so we write 1 over 1. Then we will find the LCD the way we have in previous sections. Make sure to ask your instructor or look back at the previous section videos in order to find the LCD. And we see here the LCD would be 6x. Now what I like to do before we go any further is set the least common denominator equal to 0 to determine what values I cannot have for the answer. So if we say 6x equals 0, we divide both sides by 6, we get x equals 0. This is a bad solution. We do not want x equals 0. If in fact we do get that as an answer, we have to toss it out. Now that we have a least common denominator, we've determined what values we cannot have as a solution, we are going to change each fraction so that its denominator is 6x. To do so, we would have to multiply the first fraction times 2 in the numerator and denominator. The second fraction, 1 over 1, would have to be multiplied by 6x in the numerator and denominator. And the third fraction would need to be multiplied by x in the numerator and denominator. Once we do this, we have 2 times 5 is 10 over 6x, plus 6x times 1 is 6x over 6x, equals 7 times x is 7x over 6x. When we have an equation, and this is only true if we have an equation, not if we have an expression. When we have an equation with common denominators, we can cross out the denominators. That leaves us with 10 plus 6x equals 7x. This is an equation we would have seen back in Module 2 or 3. We can subtract 6x from each side. The 6x's cancel on the left, and we are left with 10 equals x. We look back at our bad solution, and that was x equals 0, so we're good. X equals 10 is the solution. Here's the step-by-step process that we will use normally when we're solving equations containing rational expressions. Step 1, we multiply both sides of the equation by the LCD of all rational expressions in the equation, or like I showed you in the last example, once we have an LCD for every fraction, we can just cross it out. Step 2, we remove any grouping symbols and solve the resulting equation. In step 3, you can check the solution in the original equation. Let's try another example. 1 over 2x minus 1 over x plus 1 equals 3x squared plus 3x. Before we can find the least common denominator, we need to factor each denominator. That gives us 1 over 2x, that doesn't factor, minus 1 over x plus 1, again this doesn't factor either, equals 1 over, the last denominator does factor. We have a GCF of 3x, so we factor out 3x and that will leave us with x plus 1. After we observe each denominator and use the process that was explained a few sections ago, we find that the LCD is 6x times x plus 1. Just like we did on the last example, I like to take this LCD and set it equal to 0 so that we can find the answers that are not good solutions that will make our fractions undefined. So we set the first factor equal to 0, the second factor equal to 0 using the 0 factor property. And we get 6x equals 0, which would give us just x equals 0. That will be a bad answer. We have x plus 1 equals 0. We subtract 1 from each side, and that will leave us with x equals negative 1. That will also be a bad answer if that happens to pop out. Now let's take each equation and multiply by the appropriate factors on top and bottom so that we get a least common denominator. In the first fraction, we will need to multiply by 3 and x plus 1. So if we do that, we get 3x plus 1 in the numerator over 3 times x plus 1 times 2x will give us 6x times x plus 1. In the second fraction, we already have an x plus 1. We need to multiply by the 6x. So we multiply 1 times 6x, which is 6x, over 6x times x plus 1 equals. In the last fraction, we have an x plus 1, we have an x, and we have a 3. So to get from 3 to 6, we multiply by 2. We multiply top and bottom by 2. We get 6x times x plus 1. Now at this point, we can cancel the denominators because we have an equation with common denominators. Before we write down the next step, we would distribute the 3 to this binomial. And now we have 3x plus 3 minus 6x equals 2. We combine like terms, and this becomes negative 3x plus 3 equals 2. We subtract 3 from each side of the equation, and we are left with negative 3x equals 2 minus 3 is negative 1, so we divide both sides by negative 3. The negative 3's cancel on the left-hand side, and on the right-hand side, a negative divided by a negative is a positive. So x equals 1/3. We go back and we look at our bad solutions, x equals 0, x equals negative 1. Our solution is not a bad solution, so we're good to go. Let's try another example. 1 over x minus 1 equals 2 over x plus 1. Here, each denominator is already factored. So with the LCD, we have one factor of x minus 1 and one factor of x plus 1. Now, if we set the LCD equal to 0, x minus 1 times x plus 1 equals 0, we find that the bad answers are x equals 1 or negative 1. Those will give us undefined fractions. So let's go back and change each fraction so that the LCD is x minus 1, x plus 1. We will multiply the first fraction times x plus 1 in the numerator and denominator. We will multiply the second fraction times x minus 1 in the numerator and denominator. When we do so, x plus 1 times 1 is just x plus 1 over x plus 1 times x minus 1. And that equals, on the right-hand side, we're going to distribute the 2. So 2x minus 2 over x plus 1, x minus 1. At this point, because we have an equation in common denominators, we can cross out the denominators. And we are left with the equation x plus 1 equals 2x minus 2. We now move our x's to one side, constants to the other, and solve. So let's subtract 2x from each side. The 2x's cancel on the right. We're left with negative 1x plus 1 equals negative 2. We now subtract 1 from each side of the equation. That gives us negative 1x equals negative 3. And we divide both sides by negative 1, and we're left with x equals positive 3. Let's try another example. 12 over 9 minus a squared plus 3 over 3 plus a equals 2 over 3 minus a. So let's start by factoring each of these denominators and then finding the LCD. This will become 12 over, if we notice, 9 can be rewritten as 3 squared, so now we have a difference of squares factorization. And that will become 3 plus a, 3 minus a. So 12 over 3 plus a times 3 minus a plus 3 over 3 plus a equals 2 over 3 minus a. Now at this point we can notice that the LCD is 3 plus a, 3 minus a. And if we set the LCD equal to 0, we find that our undefined values will be a equals negative 3 and positive 3. If a turns out to be either of those values, that is a bad solution. Let's now go through the process of multiplying top and bottom of each fraction by the necessary factors so that we have a least common denominator all the way throughout. In the second fraction, we will need to multiply top and bottom by 3 minus a. In the third fraction, we will need to multiply top and bottom by 3 plus a. Once we do this, we see that we have a common denominator all the way throughout, and I'm going to go ahead and cancel it on this step. That leaves us with 12 plus, in the second term, we're going to distribute the 3 to the 3 and the minus a. That will give us 9 minus 3a equals, let's also distribute the 2, 6 plus 2a. At this point, we combine like terms. 12 and 9 will give us 21, so 21 minus 3a equals 6 plus 2a. We now move both constants and variables so that we have variables on one side, constants on the other. We can do this all in the same step if we choose to, or we can do it one step at a time. Let's subtract 2a to the left-hand side, and that will give us 21 minus 5a equals 6. We can now subtract 21 from both sides of the equation. That'll give us negative 5a equals negative 15. Now we divide both sides by negative 5, and we get a equals 3. So we take our answer and look back at the answers that would give us a no solution, and we see that those would be negative 3 or positive 3, exactly what we have as an answer. And so we have to cross out this answer because it would make our fractions undefined, or at least some of the fractions undefined in the original. And since we have no other answer to fall back on, we would say we have no solution to this equation. Let's try another example. 6y over 2y plus 6 plus 9y minus 3 over 3y plus 9 equals 7y plus 2 over y plus 3. As we have before, let's start by factoring each denominator so we can find the least common denominator. So the first fraction is 6y over the GCF of the denominator is 2, so 2 times y plus 3 plus 9y minus 3 over the GCF is 3, so 3 times y plus 3 equals 7y plus 2 over y plus 3. Now here, if you chose to factor out the GCF of the numerator in the second fraction and possibly simplify numerators and denominators where possible, that's perfectly fine. And in all actuality, it may make the problem easier to do. So let's go ahead and do that. If we look at the first numerator and first denominator, 6 divided by 2, 2 goes into 2 once, 2 goes into 6 3 times. So this would reduce to 3y over y plus 3. The second numerator, let's just do this off to the side. The second numerator has a GCF of 3. This will become 3 times 3y minus 1. So we rewrite that as 3 times 3y minus 1, and we see that the 3 in the numerator and the 3 in the denominator would cancel. So this would become plus 3y minus 1 over y plus 3. And on the right-hand side, there is no factoring that can be done, so just 7y plus 2 all over y plus 3. Now at this point, we see that we have a common denominator. So the LCD is y plus 3. If we set that equal to 0, we get our only bad solution is y equals negative 3. We do not want that at the end. Now that we have the least common denominator and an equation, it's only true if we have an equation. We cancel out the denominators, and we work with the resulting equation. So we're left with 3y plus 3y minus 1 equals 7y plus 2. We combine like terms on the left-hand side, and this gives us 6y minus 1 equals 7y plus 2. We move our y variables to the left-hand side. So we subtract 7y from each side. We're left with negative 1y, or negative y minus 1 equals 2. We now add 1 to each side of the equation. That gives us negative 1y equals 3. Now if we divide both sides by negative 1, we get the answer y equals negative 3. But if you remember, that was the only solution we could not have because that gave us an undefined fraction. So this is a bad solution. Since we have no other solution, our answer is no solution. Let's try one more example, and in this example, we are trying to solve a rational expression with many variables for one specific variable. So let's talk about the process we would use to do that. The first thing we want to do is clear the denominator, and we are able to do that by multiplying both sides of the denominator, or essentially finding a least common denominator. So if we do that, we have t over 1 equals 9u over b plus 3, and so our LCD would be b plus 3. In this example, we would need to multiply the first fraction by b plus 3 in the numerator and denominator. When we do that, we have, if we distribute the t, we would have b times t plus 3 times t all over b plus 3 equals 9u all over b plus 3. Because we have an equal sign and common denominators, we can cancel the denominators. And we are left with bt plus 3t equals 9u. Now we have to go through the steps that we would normally go through when we had variables and numbers to solve for b. So we subtract 3t from both sides. 3t's cancel on the left side. We're left with bt equals 9u minus 3t. To continue isolating b, we divide by t because we were previously multiplying. And the answer is b equals 9u minus 3t over t. Let's try another example. Here we have d equals h minus p over y. And we want to solve for y. Just like we did in the previous example, we will need to get a common denominator. To do that, we'd write d over 1 and h over 1. And because we have 1's and a y, the LCD will equal y. So in the first two fractions, we need to multiply by y in the numerator and y in the denominator. And when we do so, we have a y times 1, which is just y, in each denominator. So we can cancel the denominators, and we are left with y times d equals h times y minus p. Now here's something we haven't done before. We need to get both terms that contain a y on the same side of the equation. So let's write this as dy equals hy minus p. We will subtract hy from both sides. And we're doing this so we can get our y's on the same side of the equation. Now we have dy minus hy equals negative p. At this point, we notice that the left side has the greatest common factor of y. So we factor out the y, leaves us with d minus h equals negative p. And now to get y by itself, let's divide by the factor that we're multiplying by. We divide both sides by d minus h. The d minus h's cancel on the left-hand side, and we're left with y equals negative p over d minus h.